Hello everybody, this is Sif Habashi, an electrical engineering student who once dreamed of being a mathematician, but due to external disturbances, he managed to go into electrical engineering and he's happy with it, but from time to time he likes to get back to his passion, and now we are solving this summation because I want to do this. Well, the summation from k equal to 1 up until n of k squared. Well, to be able to do it, we need to build up the basic sums that are before this one, which is, for example, consider the summation of k from k equal to 1 up until n. Well, we know this series expanded is just 1 plus 2 plus dot 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 up until n, right? So we can do this the Gaussian way. You know this story when Gauss was young and the teacher got into the class and said, "Well, everybody, I don't want noise. Just keep adding the numbers from 1 up until 100 and leave me alone." And the teacher sat down and to sleep. And Gauss suddenly told the teacher that the sum from 1 up until 100 is just 5050. The teacher was shocked. How did you do it? Well, simply, he wrote this summation like this and wrote it in reverse order from n plus n minus 1 plus dot 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 up until 1. Look at this. 1 plus n is 1 plus n. 2 plus n minus 1 is 1 plus n. 3 plus n minus 2 is 1 plus n. 1 plus n, 1 plus n, 1 plus n, 1 plus n times. So it is n plus 1 repeated n times. And this is the sum of these two identical series. So to get one of them, we need to divide by 2. And this is the summation of k from k equal to 1 up until n. So since we got this, the simpler series that is simpler than this is just the summation of 1 from k equal to 1 up until n, and this is just simple. It is 1 plus 1 plus 1 plus 1 n times, which is n. So with these two series, we can go to calculate this monster. Well, how are we going to do it? Simply, let's consider the summation of k plus 1 cubed. What? Weird, right? The summation from k equal to 1 up until n. So k plus 1 cubed. What is this? Well, I'm struggling to calculate the summation of k squared. What can this help me with? Well, we don't want this cubed, so we subtract k cubed, right? So look at this. Expand this series. Put n equal to 1 here and here. I'll get two series subtracted from each other. The first series is 2 cubed plus 3 cubed plus dot 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 up until n cubed plus n plus 1 cubed. Right? This is the first series. Minus, let's write it here. Minus, substitute k equal to 1 is 1 cubed. Substitute k equal to 2, 2 cubed. 3 cubed. Dot 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 up until n cubed. Look at this. Subtracting this from this gives, well, this 2 and this 2 cancels, this 3 cubed and 3 cubed cancels up until n cubed. So all of this cancels all of this. The only the only stuff that we're left with are n plus 1 cubed and negative 1 cubed. Cool. So the result of this series is just n plus 1 cubed minus 1. We got the final answer to this. So what can this help us with? So we know now, that the summation of k plus 1 cubed minus k cubed from k equal to 1 up until n is just n plus 1 cubed minus 1. And we know n is just a number, k is the counter. Really trivial, right? So what can we do now? If we expand this with the binomial theorem, what do we get? We get k cubed plus 3k squared plus 3k plus 1. So the k cubed from here cancels the k cubed from here, and we're left with only a polynomial of second degree. So it is the summation from k equal to 1 up until n of 3n's of 3k squared. 3k squared plus 3k plus 1. This is equal to n plus 1 cubed minus 1, right? So now what? We just substitute this summation on the terms because we know the summation is a linear operator, like the integral. So it is 3 summation k equal to 1 up until n of k squared plus 3 summation k equal to 1 up until n of k plus, it's just n, equals n plus 1 cubed minus 1. Alright, so this is the unknown series. We know the result of this, we got it here. So it is just 3 summation k equal to 1 up until n of k squared plus 3 times the summation, which is n plus 1 over 2 plus n. This gives n plus 1 cubed minus 1. So after all of this, it's a tough thing rearranging, so we need to erase this side. So we need to get this here. Well, let's look here. We know 3 times the summation of k squared. Well, the pen is dying. So we'll keep going with the blue pen. So 3 times the summation of k squared from k equal to 1 up until n of 3 times n. Well, let's do a common denominator on the other side. So everything multiplied by 2 except for this term. So 2 times n plus 1 cubed minus 3n plus 1 minus 2n. Well, what can we do now? Well, let's think of all of this divided by 6 and delete this. So this is what we got. The only left thing is factorization to get a clean formula. Well, what do we get of getting this n plus 1 common factor from here? If we take n plus 1 common factor, 2n plus 1 squared minus 3n. So n plus 1 squared is n squared plus 2n plus 1, and subtract 3n, so, and there is a 2 outside, remember, so 2n squared plus 4n minus 3n, so only 1n, plus 2, so I think we'll get to something clean. So the summation from k equal to 1 up until n of k equals n plus 1 as a common factor times 2n squared plus 4n plus 2, right? Minus 3n minus 2n. So going on this side because I'm left-handed, divided by 6. So after this, cleaning this thing, we have, so the summation k equal to 1 up until n of k equals n plus 1 times 2n squared plus 4n minus 3n is plus n plus 2 minus 2n divided by 6. So factorizing this thing, we get, I think we're not getting anywhere. We're not getting anywhere. So 2n plus 4n, whatever, we're not getting anywhere. So it's better to get things messy. No! Damn it. We could have, okay, it's a bad way, so we could have distributed this, so we get here 2 times n plus 1 cubed minus 3n squared, distributing this, minus 3n minus 2n, we get 6n here, divided by 6, which is equal to 2n plus 1 cubed minus 3n squared minus 6n, right, divided by 6, which is taking 3n as a common factor, negative 3n as a common factor, 2n plus 1 cubed minus 3n times n plus 1. So taking n plus 1 as a common factor from here, I think we're getting somewhere. So taking n plus 1 here as a common factor, we get 2n plus 1 squared minus 3n divided by 6, and so expanding this, n plus 1 times 2n squared plus 4n plus 2 minus 3n divided by 6, negative 3n and 4n, we got this, what? I think I'm getting something wrong. No, everything's alright. Everything is alright. Something is going wrong right now. Oh my god. There is a 1 here. This is minus 1. So n plus 1 cubed minus 2n minus this. Now I get it. So there is minus 2 here. So there is minus 2 here. That's what made the problem. Minus 2. Okay. Let's do it again. You know, it's long time doing real mathematics. I know it's trivial stuff, but you know, we need to train. We need to get back. So yeah, we got it right. So now I think we're going somewhere. So because look at this, 2n plus 1 cubed minus, take a negative 3n here, times n plus 1 minus 2 times n plus 1. So you have n plus 1 everywhere, so you take n plus 1 as a common factor. And this is 3n minus 1. So we're getting somewhere. So taking n plus 1 as a common factor, we get here 2n squared plus 4n plus 2 minus 3n minus 2. So 4n minus 3n is just 1n, and these 2's cancel out. So over 6, and you get n plus 1 times 2n squared plus n, and that's it, divided by 6, which is n times n plus 1 times 2n plus 1 all over 6, which is the result that we are waiting for. This is the summation of k squared from k equal to 1 up until n. The pen went away, so okay. This is the result that we were waiting for. It's exciting remembering this cool stuff and realizing that I need to work on my skills, because I've been it's been a long time not doing tough mathematics with hand, because everything is simulations and calculators and so on. In engineering, we don't care about this logic, but I really loved it, and loving it now. I'm getting back to loving it. Thank you for watching. Don't forget to subscribe and press the like button, and share the video with somebody who would care to watch this. Okay, goodbye.